Hi everybody, it's Professor Mitchell. We're continuing with Chapter 3 on exponential and logarithmic functions. And today we're going to talk about Section 3.2, which is logarithmic functions. So here are the objectives in this section. We're going to change between logarithmic and exponential form, evaluate logarithms, use basic logarithmic properties, graph logarithmic functions, find the domain of a logarithmic function, and finally use common and natural logarithms. So we mentioned in the last section when we were talking about exponential functions, one of the properties of exponential functions is that they are one-to-one and therefore have an inverse. So a logarithmic function is the inverse of an exponential function. Remember that to create the inverse of an exponential function, one of the steps is to switch x and y. So imagine that this right here had started out as y equals b to the x. When we switch x and y, of course, we would get b to the y equals x. And that's basically the definition of the logarithmic functions. So the y exponent in this equation is a logarithm. So officially for x greater than 0 and b greater than 0 and not equal to 1, so this b is the same b as in the last section. It is the base. So same requirement as in the last section. The base has to be greater than 0 but not equal to 1. Y equals logarithm base b of x is equivalent to b to the y equals x. The function f of x equals log base b of x is the logarithmic function with base b. So while I'm thinking about it, notice that this log base b is a function. So it doesn't stand for a number. This you will never ever read this as log times x. Okay, so keep that in mind as we go forward. All right, now I think the number one most important thing to be able to do in this chapter is to switch back and forth between logarithmic and exponential form. So let's practice that now. Oh, and one other thing I want to mention, this is something I love to do in a face-to-face class. I call it the logarithm game. So going back here, notice how the logarithm is defined. Y equals log base b of x is equivalent to b to the y equals x. So this log base b of x is the exponent in this equation, b to the y equals x. So the logarithm game is very simple. When I say, what is a logarithm? You say an exponent. All right, let's try it once. What is a logarithm? That's right, it's an exponent. Okay, so when you see an equation like this, 3 equals log base 7 of x, and actually I think the way I have this set up, yeah, we're going to look at all of the examples and then all of the solutions are going to come up all at once, unfortunately. All right, so let's start with 3 equals log base 7 of x. So you ask yourself two things. Number one, what is the base? All right, we're looking at letter A. The base is 7. And then what is a logarithm? An exponent. The logarithm is the exponent, and this logarithm is 3. So when you go to write an exponential equation that's equivalent to this, it's going to say 7 to the 3 equals x. 7 is the base and 3 is the exponent. Okay, so don't look below here. We're going to try to do these one at a time. Next, we have 2 equals log base b of 25. Question number 1, what is the base? The base is b. Question number 2, what is a logarithm? An exponent. The logarithm is the exponent. This logarithm is 2. So the base is b, the exponent is 2. That means the exponential equation is b to the second equals 25. And then finally, we have log base 4 of 26 equals y. What is the base? The base is 4. What is the logarithm? an exponent, and this logarithm is y, so the exponent is y, and that means the equivalent exponential equation is 4 to the y equals 26. Pretty easy, right? Okay, so now we're going to go the other direction. We're going to take some exponential equations and write them in logarithmic form. So it works the same way. You look at 2 to the 5th equals x. Ask yourself, what is the base? The base is 2. What is a logarithm? A logarithm is an exponent, and this exponent is 5, which means this logarithm is going to equal 5. Okay, so the equivalent logarithmic equation would be 5 equals log base 2 of x. Make sense? Next we have b to the 3rd equals 27. What is the base? The base is b. What is a logarithm? A logarithm is an exponent, and this exponent is 3, which means this logarithm is going to equal 3. 3 equals log base b of 27. And then finally, we have e to the y equals 33. So this is our new friend e that we met in the last section. That doesn't even matter right now. E could just be a symbol. The base is e, and the exponent is y. So the exponent is the logarithm. So the logarithm is going to equal y. Y equals log base e of 33. If you can get that down, switching back and forth between exponential and logarithmic form, you should have an easier time in this chapter. All right, next we have evaluating logarithms. So this kind of works the same way. First we have log base 10 of 100. Okay, so there are a couple different ways you can do this. First of all, a logarithm is an exponent. It is the mystery exponent that you have to raise 10 to get 100, okay? So 10 to what power equals 100? The answer is 2, because 10 squared equals 100. The other way you can do this is you could say, well, I don't know the answer, so I'm going to call it x. That's supposed to be a regular equals, not a wiggly. Okay, and then you could take this equation and write it in exponential form the way we were doing just a minute ago. So log base 10 of 100 equals x. In exponential form would say 10 to the x equals 100. And then by inspection, as we say, which means just by looking, you can see that x has to be 2. All right, similarly, log base 5 of 1 over 125 means 5 to what power equals 1 over 125. So this one's a little harder. If you know that 125 is 5 to the 3rd, then hopefully you can figure out, because 1 over 125 is the reciprocal, that makes the exponent negative. All right, since 5 to the negative 3 is 1 over 125, that means log base 5 of 1 over 125 is negative 3. All right, let's see what's going on. Oh, wait a minute. Okay, there we go. All right, another example, log base 36 of 6. Let's see how they did this one. So again, log base 36 of 6 means 36 to what power equals 6. So you think about it, and hopefully you at some point remember 1/2 power. 1/2 power means square root. So because the square root of 36 is 6, that means that 36 to the power 1/2 equals 6. All right, here's a similar one. Log base 3 of the 7th root of 3. So this would mean 3 to what power equals the 7th root of 3? Well, if you think about writing 7th root of 3 as 3 to a power, the 7th root of 3 is 3 to the 1/7, which means the mystery exponent here is 1/7. So log base 3 of 7th root of 3 is 1/7. Okay. So some basic properties of logarithms. First, log base b of b is always 1 because imagine I just handed you log base b of b. I'd be asking b to what power equals b? Well, first power, right? 1 is the exponent to which b must be raised to obtain b. And then log base b of 1, so that's asking b to what power equals 1? That would have to be 0. Remember that special property of 0 exponents, anything to the 0 is 1. All right, and these are true for any base b, okay, as long as it's a legitimate base, right? Greater than 0, not equal to 1. Okay, so using those properties, if you know those properties, it makes these problems very easy. First, we have log base 9 of 9, and then we have log base 8 of 1. So starting with log base 9 of 9, that's asking 9 to what power equals 9? The answer is 1. 8 to what power equals 1? The answer is 0, right? Okay, and then we have these properties. These are called inverse properties. Remember that this is going back to chapter 1, the section on inverse functions. Remember that if f and g are inverse functions, that means f of g of x is equal to x, and also g of f of x equals x. So if you make one of those functions f of x equals b to the x, and you make the other one g of x equals log base b of x, you get these two properties. Log base b of b to the x equals x, and b to the power log base b of x equals x. So I think I can help you appreciate, if I can find my mouse. There it is. Found it pretty fast this time. I think I can help you appreciate at least the first property. So again, imagine that this x wasn't here, and I just asked you, what is log base b of b to the x? I'd be asking you b to what power equals b to the x? Well, gee, I guess the answer is x, right? Okay, that's the idea. All right, so let's look at some examples of that. Get my mouse back here, there we go. Okay, so log base 7 of 7 to the 8th. Again, that's asking 7 to what power equals 7 to the 8th? Well, gee, I guess the answer is 8. The other one I find a little harder to explain. It's an inverse property again. 3 to the power log base 3 of 17. So one way to think of this is, what does log base 3 of 17 do? It is the mystery power to which you have to raise 3. I think I'm writing in the spot where the answer is going to come up, but that's okay. Log base 3 of 17 is the mystery exponent that you have to raise 3 to get 17. Oh, okay. Well, when you put it that way, this thing must equal 17. It's just, you know, there's kind of 3 parts to this equation. And with what I wrote here, I was leaving out one part, and with what they wrote here, they were just leaving out a different part. All right, so log base 7 of 7 to the 8th is 8, and log 3 to the power log base 3 of 17 is 17. All right, now we have graphing. And I really like the way they do this. So we're going to start by graphing f of x equals 3 to the x and g of x equals log base 3 of x in the same rectangular coordinate system. So what we'll do is set up a table of coordinates for f of x equals 3 to the x, and we actually did that already in the last section. And then, because inverse functions just reverse the x and the y, we can just switch the x and the y to get the graph of our new function. So I just want to point out to you here, this table could very well be copied and pasted from section 3.1. We made this exact table in section 3.1. So these 4 points are all on the graph of f of x equals 3 to the x. So now if you reverse the x and the y, you get 4 points that are on the graph of g of x equals log base 3 of x. And so that graph looks like this. Remember also that when you graph two inverse functions on the same coordinate system, they are reflections of each other across the line y equals x. Another thing to point out here is I told you in the last section that the graph of an exponential function can really only look 2 different ways. It can either look like this, or if the base is between 0 and 1, it's the mirror image of that. It looks like this. So that means that the graph of your logarithmic function can also really only look 2 different ways. So that's kind of nice. All right, so now we have some properties of logarithmic functions. First of all, the domain of f of x equals log base b of x consists of all positive real numbers. So remember, in the definition of logarithmic function, we required x to be greater than 0. However, the range of f of x equals log base b of x is all real numbers. Remember, it was just the opposite for the exponential function. The exponential function had domain all real numbers and range positive numbers. So now that we're looking at the inverse function, those are switched. The graphs of all logarithmic functions of the form f of x equals log base b of x pass through the point 1, 0 because of that property that says, let me see a typo here. Because of that property that says log base b of 1, that was what was missing here, is 0. So therefore the x-intercept is 1, and there is no y-intercept because x equals 0 is not in the, sorry, mouse disappeared again, because x equals 0 is not in the domain of the function. If b is greater than 1, for example, for example, this logarithmic function, then f of x equals log base b of x has a graph that goes up to the right and is therefore an increasing function. However, if b is between 0 and 1, then f of x equals log base b of x has a graph that goes down to the right and is therefore a decreasing function. Let me see if I can show that to you real quick. So let's see. Okay. So let's start with our exponential function with base between 0 and 1. This is not going to look pretty because I'm, oh darn it, I yammered on too long and my pen disappeared here. Okay, so now I have that back. Okay, I'm just going to do it. It's probably not going to look very good. Okay, so your function looks something like this. Yeah, better than I thought it might come out. Okay, and so your corresponding, let's see, what's a color I haven't used here yet? How about green? Your corresponding logarithmic function would be the reflection of this curve across the line y equals x, and so that would look something like this. It would really be a reflection across the x-axis of the other logarithmic function. It would look like this. That's supposed to, actually, hold on, because that's supposed to go through, it's supposed to go through the point 1, 0. Okay, so let me, okay, something like that. Okay, so that is a decreasing function. All right. Okay, and then finally, number 5, the graph of f of x equals log base b of x approaches but does not touch the y-axis, which means the y-axis, aka x equals 0, is a vertical asymptote. Logarithmic functions have a vertical asymptote. All right, domain of a logarithmic function. So the domain of an exponential function of the form f of x equals b to the x includes all real numbers, and its range is the set of positive real numbers. And again, because the logarithmic function reverses the domain and the range of the exponential function, the domain of a logarithmic function of the form f of x equals log base b of x is the set of all positive real numbers. Oh, darn it, there is a really bad typo here. Sometimes I notice these ahead of time and sometimes I don't. This is supposed to say log base b of g of x. Okay, the domain of that function consists of all x for which g of x is greater than 0. So this will make a lot more sense when we do an example. So why don't we do one right now? Okay, there we go. So we want to find the domain of f of x equals log base 4 of x minus 5. So what they were trying to explain on the previous slide is that whatever is inside that logarithmic function has to be greater than 0. So in this case, x minus 5 has to be greater than 0. And of course, if x minus 5 is greater than 0, that means x is greater than 5. So the domain of this function is the interval from 5 to infinity, not including 5. And there's another nice way to think about that. Remember that when you take a function and replace x with x minus 5, that shifts the graph 5 units to the right. So my original logarithmic function, f of x equals log base 4 of x, would have looked, oh God, that looks terrible. Oh, I can't stand that. Let's get rid of that. Let me try this again. It's gonna look something like, okay, that's a lot better. All right, I was trying to go too fast. Okay, so when you shift that 5 units to the right, you end up with a graph that looks like what you see there. All right. All right, getting close to the end here. So 2 very special logarithmic functions, and actually these are the only 2 that you have on your calculator. First of all, we have the logarithmic function with base 10. That is called the common logarithmic function, or common log. And the function f of x equals log base 10 of x is usually just written f of x equals log x. So if you see log x with no subscript, you can assume that the base is 10. All right, so here's a real life example using common logarithm, and I am also going to show you how to put this in your calculator. The percentage of adult height attained by a boy who is X years old. This is kind of fun. If you have a son, you know, that's 8 or 10 or 12, you can use this formula to predict how tall he will be as an adult. The percentage of adult height obtained by a boy who is X years old can be modeled by f of x equals 29 plus 48.8 times log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. So the question is, approximately what percentage of his adult height has a boy attained at age 10? So we just have to plug in 10 for x. And when we do that, we get 29 plus 48.8 times the log of 10 plus 1, which is 29 plus 48.8 times log 11. And that comes out to approximately 80%. So now I'm going to bring up my calculator just to show you what that looks like on there. The log buttons are pretty easy to figure out, I think. Okay, where is my, there we go. Okay. Okay, so 29 plus 48.8. You see log there right next to the number 7. And now just put in your 11. 79.82 approximately, and they're rounding that to the nearest whole number. So if you have a 10-year-old son, you can measure how tall he is, and that's probably 80% of the height he will reach by the time he's an adult. Okay, and of course, it's just an approximation. Okay, so let's go back to here. All right, that is your, oh, okay. A little more about common logarithm. This is technically nothing that we haven't talked about already. It's just written using the special notation. So earlier in this section, we talked about these properties of log base b. If you write them in terms of log base 10, they look like this, because remember, we usually don't write the subscript 10 when we're talking about common logarithm. All right, and that brings us to natural logarithms. So the natural logarithmic function is the logarithmic function with base e. So in the last section, we talked about f of x equals e to the x. This is the inverse of that function. This is the simplest logarithm to work with in calculus, believe it or not. That's why it's called natural. The function f of x equals log base e of x is usually written f of x equals ln of x, natural logarithm. Okay, properties of logarithms written in terms of natural log. All right, so if you make your base e here, what happens is we always write log base e as ln. So these are just specific, these properties written specifically for natural logarithm. All right, and one application involving natural logarithm. When the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times natural log of x minus 11.6. So notice that there are no parentheses around x minus 11.6. So that means take the natural logarithm first and then multiply by 13.4. And the very last thing you'll do is subtract 11.6. Okay, so that function models the temperature increase after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. All right, so that just means 30x, 13.4 times natural log 30, and then subtract 11.6, comes out to about 34 degrees. Which means the temperature will increase by approximately 34 degrees after 30 minutes, which is why if I'm out at Safeway or Target and I see a dog in a car with the windows rolled up, I am breaking that window first and I'm asking questions later, all right? Sorry, not sorry. Let's go back to the calculator one last time. Oh dear, okay. All right, so let's see. Okay, yeah, it went 13.4. Natural log next to the number 4. 30. Close the parentheses and then subtract 11.6. Comes out to 33.976, which they rounded off to 34. And I think, yes, that's going to do it for section 3.2. We'll see you next time for 3.3.